but today we are here to learn. And so I'm going to pass the microphone over to Charlie Orsak, an advocate for climate solutions and a retired pediatric psychologist who has experience in the mines. From you. We're so glad to hear from you. Thank you for being here.
Well, it's really wonderful to be here, and this full house is very impressive. So I have great affection for Ely based on a number of experiences. I used to work for Voyager Outward Bound School. Voyager Outward Bound School. And then there was one memorable Christmas in 1972 where I went to every bar in Ely dressed as Santa Claus, which was more fun than any person, and it's a very cheap way to go out. The other thing that Lacey mentioned is I used to work for Erie Mining. I was a laborer and then a foreman. And so when I heard about the topic of green or clean steel, that is not the first word that popped into my mind as a miner. Anything to do with clean or green. But I got more and more intrigued. So I entered into this topic as a skeptic, and I've come out a believer. And so let me introduce, it's going to be a team of us today. Lacey, there we go. It's going to be a team of us speaking today. I'll introduce everybody. This is, raise your hand, Mike Oberon. He's a retired veterinarian and climate advocate from Two Harbors. Jeff Hansen, your own Jeff Hansen from Babbitt. Online, we're going to have Eric Enberg, who's a family physician from Duluth. And the only true expert who's not a citizen on our team is Russ Matson, who's an electrical engineer that's semi-retired from MP&L. And he's doing electrical engineering stuff at the moment. So he's not going to be with us, but he's one of the presenters here. Now, I wanted to just share this as the Ely inspiration. We're here to talk, of course, but we're here to listen. So we're going to try to leave ample time for questions and discussion at the end. So I hope to speak for 40 or 45 minutes, then there'll be 15 minutes of question time. And so I thought this was an apt quote about the importance of listening. And we'll try to do that. A little bit about Citizens Climate Lobby. It's a volunteer and it's nonpartisan. That's an important thing to understand. All citizens, all volunteers. There's over 400 chapters in the United States. There's international chapters, and there's several 100,000 members. And what CCL does is advocate for effective, sustainable, and fair climate solutions. And the core value, actually, at CCL is we see conversations and agreements, things we can agree on and work together on, not arguments and contention. And if you came to one of our meetings, there's actually a statement that's read before the meeting that outlines it's like a pledge to listen to other people, to try to understand and try to come together on these issues. Now, the national focus for CCL is carbon fee and dividend, as well as electrification, permitting reform, and healthy forests. Now, so we're from the Northland chapter of CCL. And we are interested as a group in what we call win-win-win solutions. And what we mean by that is, as a group of people for several years now, we tried to look at issues that, number one, solutions that would lower carbon emissions, but would do so on a regional basis, addressing issues that we have here, not necessarily just on the national interest, that provided sustainable economic development. Because we don't really buy into the notion that it's jobs or the environment. It's possible for it to be both. So we want things that provide sustainable and responsible economic development and that protect our northern Minnesota way of life. That's very important to us as well. So what we've landed on, and it's taken several years actually, is this issue of greening or decarbonization of iron mining and steel. And the way we think of it is we're trying to think of a start to finish reimagining of this process. And so we've been presenting to various groups on this topic, and we're lucky to be here today. Now, that sums up the attitude of our group. Well, I had the pleasure of drinking root beer with Dorothy on several occasions. And that's our attitude, which is, let's find the solution, let's all work together, and let's get to work on it. And so we almost have a rule in CCL about no complaining. All right, so why is this important? Why should we even spend time talking about this? If you look at global CO2 emissions, steel production accounts for about 8%. Transportation accounts for 14%. So it's a lot of CO2 emissions, and it's worldwide. Now, the race to decarbonize is underway. If you look at, is that better? Can you turn it up? Yeah, I'm sorry. I'm not getting too much feedback. Go ahead. Usually that's not a problem for me. Standing in a podium for an Italian is a hard thing. No, it's not working. Okay. Can people hear me?
Yeah,
Should I keep going? Or should I wait?
speak loud.
I can do that. All right. So the race to decarbonize is underway. If you look across the steel industry, for example, they've set goals and they have stated goals of decarbonizing. Now, of course, we always have to be leery of greenwashing, but there's the intent out there. The best we can tell is it's sincere intent. Now, the thing that is good to realize is that if we're going to be in a decarbonized world, a decarbonized steel, here comes the new microphone. There we go. That sounds like it's working.
Crazy for a moment.
Yeah, let's not try to squeaky. There we go. How's that? Now I can hear it. There we go. All right. So we're ahead in this. If we look at the global steel production of the 7 top producers, the United States production facilities have the lowest carbon footprint in the world. It's a statistic that kind of surprised me. We also lead in recycling. A lot of the new electric arc furnaces are based on recycled steel. So we're kind of ahead of the world in that one, in that regard. Now the demand for green steel is growing, and the demand is coming primarily from the automobile industry. People don't want to buy an electric vehicle that's made with carbon intensive materials. And so this is where I think personally that the companies are sincere about this desire, because their customers are requesting it or demanding it. And so if we're able to accomplish this, if we're able to decarbonize steel, what will be gained? Well, lots and lots of carbon will be mitigated, of course. There'll be lots and lots of jobs and economic development. And our future generations will be better off because of our contribution to mitigating CO2.
There's a message that came through that said Russ is online and available.
Oh, great. So I take it back. Russ is not in the building. Russ Matson is the electrical engineer. That's good. I'm off the hook for doing his part. That's good. So that begs the question, why not here then? Why not on the range? Why not in this area? And why can't we participate in this? Because we have all the ingredients. We have natural resources. I mean, after all, this is where the ore is. We have skilled workers and the training infrastructure. We sit, and Russ will explain this in detail, we sit in a very advantageous place on the electric grid. And transportation, we have Duluth, we have the harbor, we have the railroad. And again, we'll talk more about this, we have access to renewable energy today. And I think as part of the legacy here for the range is that this wouldn't be the first time the range had to pivot. I mean, taconite used to be considered waste rock until they found a way to concentrate it. So what's the recipe for green steel? This is what we're going to talk about. So the first thing is you have to have new ways of making steel or improve the old ways to decarbonize. All right, and Eric Enberg is going to talk about that. But then if it's truly going to be green, that whole process needs to be powered by renewable energy. Carbon is used in steelmaking in two ways. It's used to reduce, there's a chemical reactant that reduces carbon ore, and it also provides heat. So you have to find green alternatives to that. The energy part is through you. You have to be able to find the renewable energy and get it here. And that's what Russ talks about. And then for renewable energy to be useful, you need to be able to store it. And that's what Mike's going to talk about, is storage. Very interesting topic. And then if you're going to do this responsibly, then you're going to have to address issues like sulfate pollution. And that's what Jeff's part of this is, about mitigating sulfates and other environmental issues. So getting back to what I was talking about, we're thinking about this as a complete reimagining of how we do business. And so now, could we get Eric? He's online.
I am here.
There he is. Can you hear him?
I can hear everybody. Yes, that's right. You're all looking beautiful today. It's very nice. Oh, there was a little bit of humor there. Okay, there was a little bit of laughter. Okay, good. All right. So, well, let's just go ahead and get into it. We'll go ahead and change the slide here, and we'll talk about various ways that steel is being greened up. The first one is going to be molten oxide electrolysis. You know, for 100 years, we've been producing a lot of aluminum, which is like iron, only found combined with oxygen by just running gobs of electricity through it, and you get aluminum out of it, and oxygen is a waste product. Well, some pretty smart guys over at Massachusetts Institute of Technology, or MIT, thought, well, why don't we go and try to apply that to the making of steel? Because it's kind of the same thing. And so they've been working on this and now are entering into a pilot project. And it works. You actually can create steel out of this process. What you need, though, is you need cheap, renewable electricity. Electricity from wind and solar is the cheapest electricity that we have available to us now. But if we can get this process to work and have it commercialized, it will be very modular, which means that on the Iron Range, it can literally be located at the mouth of the mine and then make steel at that location. It's non-toxic. The only waste product is oxygen, and it allows for the value-added steel manufacturing on the job, which, you know, leaders on the Iron Range have wanted for 100 years. And this is one of those technologies that might just make it happen. Because it would use renewable electricity, it would be immune from things like carbon pricing, for instance. So it would be a very stable way to produce steel. The commercialization is probably going to be in a couple of years, and potentially, because you have the steel making right there on the range, you can then begin to semi-finish it, if not finish it. Potentially a large number of diverse jobs on the range could be obtained with this technology. Next slide, please. The next technology I want to talk about is low temperature iron. Now, low temperature iron, you know, when you think about steel making, you usually have in your mind a very energy intensive, red hot, molten, you know, sparks flying all over the place kind of a process. And that historically is how it had to be done. You had to take coking coal and you had to mix it with the iron, fire it up, and the heat would dissociate the iron from the oxygen, and the carbon in the coking coal would steal the oxygen and be blown off as carbon monoxide or carbon dioxide. This technology goes about concentrating that iron and getting it pure in a very different way. It uses a low temperature, something that be roughly twice body temperature. It uses an acid to liberate the iron, and then it uses an electric field to electroplate the iron out. And what you see there on the right are the actual plates of iron that are produced in this process. From there, since you have iron plates that are now 99.9% iron, you can feed them into an EAF, or electric arc furnace, which is the predominant way in which steel is now made in this country, as Charlie alluded to, through a recycling process. You just add this to the recycled steel that you have going into the furnace anyway, and it melts down and makes steel. Interestingly enough, you can also liberate other elements such as copper, aluminum, magnesium, and silicon, all very useful things that can then be sold on the market. The pilot is going to be done in Pueblo, Colorado, where an electric arc furnace is already located. So that's going to be the first pilot phase where they're going to be working out some of the kinks to this process. Okay, next slide, please. The next technology is direct reduced iron with hydrogen. Now, direct reduced iron is already produced with natural gas, and it does the heavy lifting of the steelmaking process in which most of the energy is used. Getting oxygen to separate from iron is the big lift as far as energy consumption is concerned. And that now can be done with hydrogen instead of with natural gas. Now, the hydrogen, in order for this to be green steel, of course, has to be produced from green electricity. If you have green renewable electricity, then the hydrogen that is produced by running that electricity through water and in a process known as electrolysis, which releases hydrogen from one electrode and hydrogen or oxygen from the other, that hydrogen can then be used to heat up the iron ore, separating out the oxygen and stealing away with it when it combines with the hydrogen to form water vapor. This produces sponge iron, and you can see in that picture to the right that the person is holding a briquette of sponge iron. That came from the plant, the hybrid plant, which is shown somewhat fuzzily in the background. And the hybrid plant in Sweden is now shipping steel. That's green steel that's now being used. If memory serves me correctly, I think Volvo is using that in its electric vehicles. Next slide, please. The next technology that I want to talk about is called thermochemical reduction oxidation. Yeah, just go ahead and say that 10 times fast. But it really is something that is going to probably be a very big contributor to the greening of the steel industry, if for no other reason than it allows the steel industry to bolt on a process to their existing blast furnace / basic oxygen furnaces, and really reduce the amount of carbon emissions that come from their plants. It's kind of a complex type of thing. I have helpfully put a Rube Goldberg machine there on the right, because literally the schematic for this process is at least as complicated as the Rube Goldberg machine is right here. But the basic idea is that you take a standard steelmaking facility, a blast furnace, basic oxygen furnace type of thing, and you use a vessel that has perovskite crystals in it. Now, perovskite crystals this is not something that your crazy aunt wants to put on your chest when you have a cold or something like that. This is actually a very common mineral which has an interesting property. Well, they have a lot of interesting properties, actually. They're being studied for many different reasons. But perovskite crystals have one thing that's very useful for this process, and that is that they have a strong affinity for oxygen. They will steal oxygen from some other compound, and then when they're saturated, you can then pump the air out, and in a low oxygen environment, these perovskite crystals will release the oxygen. This is the basis for this process. When you have when you have the blast furnace and you're producing carbon dioxide, That carbon dioxide then is run over the crystals. The crystals steal an oxygen from the carbon dioxide, and the carbon monoxide goes back into the blast furnace where it steals more oxygen from the iron. And over and over and over this goes for about 24 hours until the perovskite crystals are saturated. At that point, you then stop the process, evacuate the air, and the oxygen is released from the crystals. That oxygen then goes to the next part of the process, known as the basic oxygen furnace, where a bit of oxygen is used to get rid of the last couple of percent of carbon that might be mixed in with the now raw steel, which is known as high carbon steel, and makes it into low carbon steel, which is the more desirable form of steel in most cases. The oxygen there's actually an excess of oxygen, and that excess oxygen can then be sold as an industrial oxygen source. Now, from the steel maker's standpoint, this has a lot of good things to it. It cuts the cost of making the steel in half because you don't have to use expensive metallurgical coking coal to make steel anymore. And it results in a 90% CO2 reduction for making the steel. The only unfortunate thing about this is that it's still on the lab bench. This was developed in Birmingham, England, and they're still trying to get it into the pilot stage. But it is expected that within the next couple of years, this process is going to be bolted onto steel mills probably around the world, probably. Okay, next slide, please. So then there's a question. Well, where to experiment with these sorts of technologies? The old Esser plant has a massive electrical supply. And when you think about it, that's exactly what molten oxide electrolysis or low temperature iron need. And it might make an excellent place, an excellent home for some semi-finished steel production up on the range, which again, would really be a great way to add an awful lot of diverse jobs to the mining industry. And I think that's it for me. I believe Russ is next.
Yeah, can everyone hear me? Hello? Can you hear me? I guess not.
Yes, I can. Yes,
Oh,
thank you.
Okay. Well, I'm Russ Matson, and I'm going to give a short presentation on all the opportunities we have because of legacy situation northern Minnesota. We can go on to the first slide. Get started. Well, first, some background information. The driving force behind our opportunities is the growth in renewables, solar and wind. Recent data from the EIA, the Energy Information Agency for the US, shows intermittent wind energy production amounted to 13.6% of the energy production as of February of this year. And projections by NREL, which is the National Renewable Energy Laboratory, and others indicate wind and solar will double by 2030, reaching 1/3 of the United States energy supply. Because of the intermittent nature of renewables, energy storage is an absolute necessity. Storage will be necessary for arbitrage, a lot of functions, load shifting, spinning reserve, frequency control, deferral of various projects or being able to do the projects, and also curtailment, which what happens now is that at certain times of the year, generations, certain times of the day, wind and solar are curtailed because there isn't the demand for them. And just to give you an impact of that, our energy storage situation, in 2018, 4 billion megawatt hours, which is a lot of energy, that's the electric energy the United States consumed. There are only 431 megawatt hours of energy storage. Or put another way, there's the ability to store much less than 1% of the energy power generated today, or less than 10% of the renewable energy that's produced today. Today, essentially, natural gas is used to fill the gaps relating to intermittency, and that's why you see there's the coal has gone away, and coal plants are closing every day, but they're being replaced by natural gas facilities because this intermittency has to be addressed. Okay, on this slide, the most likely candidate to meet this requirement is knowledge of energy storage. To meet the energy, there's various technologies of energy storage. Today, the United States has 30 gigawatts or 30,000 megawatts, however how you want to look at that. For instance, Boswell is about 600 megawatts, if you're familiar with the Boswell plant in Grand Rapids. So this is how much energy storage there is in the United States. But today, the vast majority of that energy storage is in pumped hydro. 92% of the energy storage that we have in the United States is pumped hydro. There are 43 such plants today in the United States. It's a mature technology. It's been around for over 100 years. Looking at pumped hydro versus other forms of energy storage, such as lithium-ion batteries, which by far the most popular method of energy storage today. That's what's being installed everywhere at solar farms. It's used in 90% of the battery installations, but it has severe limitations, which include supply chain issues, material sourcing, competing uses for lithium, and its discharge cycle and cost. The discharge cycle is 2 to 4 hours, which is a very short time. Next slide, please. There have been recent studies done by the University of Minnesota via the NRRI looking at the feasibility of pumped hydro in northeastern Minnesota at abandoned mine sites. 9 such sites have been identified for further study. Michigan Tech has also completed studies nationwide on utilizing abandoned underground mines for pumped hydro, which has some advantages and disadvantages as well. This slide shows an existing pumped hydro location in Ludington, Michigan. It's on right off Lake Michigan, up on the sand dunes there. This was built, I believe, about 50 years ago. Next slide, please. There are other energy storage technologies that have also been studied by the University of Minnesota. One such technology is compressed gas energy storage. In this method, air is compressed, stored underground, and released to the surface when needed to drive a turbine. There are 2 such large facilities in operation today. I believe one is in California and the other in Alabama. They are actually fairly large facilities. And next slide, please. This shows a diagram of how compressed air storage works. It's basically storing it underground, and then what's advantageous, one has to have the correct geology to be able to do that. Okay, next slide, please. There are other technologies as well which are suitable to northeastern Minnesota, such as gravity storage. Weights are lifted to a height above grade and released when the energy is needed driving a turbine. These have the advantage of being able to be located almost anywhere, even in existing buildings, and easily constructed, like I say, in almost anywhere. It's simple, efficient, and like I said, they can be located anywhere. This particular one is by a company called Energy Vault in Switzerland. Next slide, please. This same technology can also be used raising and lowering the weights in an underground mine. And this particular installation is in the Czech Republic, and an existing fuel facility. It has an advantage of kind of being out of sight. The mine's been there for an abandoned maybe for 20 years or longer, and you can locate the gravity storage there. Next slide, please. Yes, and this is the real interesting thing. We're in the nexus of the grid here in northern Minnesota that people don't realize. The facilities that come here, we're able to take advantage of all this renewable energy and the storage because of the existing legacy transmission lines built for other reasons, some 40, 50 years ago, many serve lines and many passing through to deliver energy to Excel or into Wisconsin. But there are a couple of 500 kV lines from Manitoba Hydro into Minnesota, a 345 line from Minnesota into central Wisconsin. There's multiple 230 lines which connect Minnesota Power, Great River Energy, Minn Kota. And there was also two more transmission lines, 345 being planned by Great River Energy and Minnesota Power from northern Minnesota, north central Minnesota into southern Minnesota. And there is also two HVDC lines, which is extremely, and they are not that common worldwide. So we have these in place. We also have the transportation infrastructure, the ports, the highways, and the rail. Once again, I have to emphasize, this is extremely unusual to have all these facilities in one place, and it's a combination of who our neighbors are and what was built to serve the mines and to sell power into neighboring states and customers. So it's a very unique position. And if we go to the next slide, please. Obviously, to have a green environment, you have to have green and renewable energy. And Manitoba Hydro has identified an additional 4,300 megawatts of hydro. This is at existing facilities, things that have already been constructed, or the turbine hasn't been put in some cases, but the facilities are already there. It's not like they're have to build another dam. So there's a lot of potential green renewable resources available for Manitoba. Just to give you an idea of the magnitude of power that they export already to the United States, mostly to Minnesota, is that they in 2019 they exported 7 terawatt hours, which is enough to serve 6 cities the size of Duluth for 1 year, provide all the electric needs. And in addition to this, there is also wind resources available from North Dakota and southern and western Minnesota. So we're in a unique position to get the renewable energy and store the renewable energy and use this for making green steel, for instance. And I believe that's the end of my slides, and I think we go next to Mike.
Thanks, Russ. How about
This
that
one
one?
is less.
Okay, thank you. I'm Mike Overend, and hearing okay in the back. I was thinking when Charlie introduced himself that I too met the root beer lady in 1967. So I'm going to talk about Form Energy's iron air battery, and thank you for allowing me this opportunity to talk to you about this. Primarily, I'm focused on trying to bring manufacturing of this battery to Minnesota because it offers a unique economic development opportunity for our Northeast Minnesota communities. It offers permanent, strong job growth for Minnesota iron mining industry. There are sustainable, new, environmentally friendly manufacturing jobs related to manufacturing this on the range. This does not require controversial metal resources or unreliable supply chains. And these batteries are a critically important climate solution. And I'll just say that whoever can control the most clean energy wins. Next slide, please. Our global energy system has a major problem. In 2022, over 60% of our global electricity came from burning dirty and expensive fossil fuels. This is a huge source of pollution, waste, and extra cost. This is a major source of greenhouse gas emissions causing global warming, which in turn contributes to massive severe weather-related losses, floods, droughts, fires, disease, crop failures and famine, and devastating conflicts. It's a major contributor to air pollution, causing chronic respiratory and heart disease. The Harvard School of Public Health in 2021 noted that air pollution from burning fossil fuels like coal and diesel was responsible for about 1 in 5 deaths worldwide. Burning fossil fuels is causing a major risk to our future from global economic damage and inflation. And at the same time, it's destroying our environment and our health. Next slide, please. To correct this, we must transition to 100% clean, cheap, renewable energy as soon as possible to meet our future energy needs. Converting from fossil fuels to 100% renewable electricity, combined with the process of beneficial electrification. Folks here familiar with that? Okay, that's the process of turning everything that used to be run by fossil fuels into running it by electricity, because it's a lot more efficient and it's a lot cleaner. So by combining beneficial electrification of all of our machines, everything that we use in our lives, that will eliminate 80% of all greenhouse gas emissions. Unfortunately, the sun doesn't always shine and the wind doesn't always blow. And the majority of renewables, wind and solar, are intermittent energy sources. So in order to provide 24/7 reliability of renewable energy, we need a multiple day utility scale battery. Next slide, please. In 2017, Form Energy identified the need for a cost-effective multiple day utility scale storage battery. And Form created a cost-effective, clean, and scalable solution to solve this intermittency problem with their iron air battery. This battery storage provides power for up to 100 hours, and it makes renewable energy the clean and cheap 24/7 reliable energy source that we need for both our routine and our emergency energy storage needs. Next slide, please. Form Energy's iron air battery is a unique technology which instantly provides up to 100 hours of continuous power for communities and industry. It uses abundant, affordable iron products originating from Minnesota. It uses safe, non-flammable design and recyclable, non-toxic components. It's flexible, modular, and scalable to meet the variable energy storage needs of any major electric utility. It makes renewable energy the new 24/7 reliable power for the world. It allows the development of other new green industries, which require 24/7 clean energy sources, just like what Eric was talking about earlier. It allows excess, cheap, clean, renewable energy production not to be wasted, but instead to be stored for later use when it's needed. Next slide. The iron air battery uses the common chemical reaction of rusting iron-based metal using water and oxygen from the air to instantly release stored electricity for up to 100 hours. When the battery is recharged, the rust is converted back into iron metal. The only byproduct is safe oxygen released into the air. This process provides instantly available, cheap, clean, reliable electricity from our renewable energy resources. Kind of a tongue twister. This technology is designed to deliver energy storage at 1/10 the cost of current lithium-based storage batteries that utilities are using. Next slide, please. Iron air batteries are an important tool for achieving Minnesota's new goal of 100% clean electricity by 2040. Minnesota's 100% clean electricity goals give our communities a competitive advantage for participating in the clean energy economy. These batteries allow all utilities to meet the 2015 Paris Agreement goals for 100% clean energy by 2050 using renewable energy. They allow utilities to economically justify earlier retirement of the dirty and expensive fossil fuels we currently use to power our lives. They create a critically important renewable energy climate solution for electricity consumers around the world. And combined with beneficial electrification of all of our machines, they eliminate the production of 80% of our global greenhouse gas emissions causing global warming. Next slide, please. Northeast Minnesota has the unique resources. Oh, there we go. Northeast Minnesota has the unique resources which are perfect for Form Energy to manufacture their iron air batteries right here. We've got the skilled labor, the iron ore, and the potential to make DRI or direct reduced iron pellet production right here on the range. We have the advanced electric grid and transportation infrastructure that Russ just talked about to meet Form's needs for supply, manufacturing, and distribution. We have the potential to create other green industry locally that would directly benefit from the use of iron air batteries in our local electric grid. Northeast Minnesota is a perfect home for Form Energy manufacturing of their iron air batteries. Next slide. In December of 2022, just a few months ago, Form Energy announced the construction of their very first manufacturing facility, which will be in Weirton, West Virginia. Form Battery Manufacturing brought 750 new jobs to that community and $760 million in investments that will benefit every family that lives there. Form Energy has raised a total of $923 million in funding as of February of this year. They've secured multiple projects with U.S. utilities, which are designed to provide proof of concept of their battery technology. They will have an enormous market demand around the globe, and additional manufacturing facilities will likely be needed very soon. Battery storage is a new energy sector that's predicted to have enormous growth. And one analysis companies stated that we expect U.S. storage market to install almost 75 gigawatts between 2023 and 2027. So in 4 years, that's the equivalent to about 75 major coal-fired power plants worth of storage. Last slide, please. Manufacturing of Form Energy's iron air battery offers a unique economic development opportunity for Northeast Minnesota. And this manufacturing creates a large demand for DRI pellets that are used in these batteries. That's going to support many permanent iron mining jobs and the potential for DRI production right here on the range. It'll provide jobs to construct a battery manufacturing facility here. It'll provide sustainable manufacturing jobs for the batteries themselves here on the range. It also makes other new clean energy economy industries possible, like green steel that Eric talked about. These batteries are cost-effective, safe, recyclable, scalable. They don't need controversial resources. They don't rely on fragile supply chains. And our goal in talking with you is to develop community and leadership support from you folks to recruit Form Energy manufacturing to come here, because we want to see this same unique economic development opportunity happen here on the range. And these are mining jobs that are for the environment, and they'll sustain and unite our communities. So why not ask our leaders to recruit manufacturing of this battery on the range? I'll pass this off now to your very own Jeffrey Hansen.
Gotta get my props. No, I'm gonna run it. So anyway, welcome folks. You've already learned my name is Jeff Hansen. I'm the guy in black from Babbitt.
and we'll learn why. Because I make black stuff. Okay? We're talking about sulfate remediation systems. And before we get into really the sulfate side, I want to just mention, you probably saw articles in the newspaper recently about the EPA directing big funds for finally clamping down on the taconite industry to reduce mercury in their flue gases, right? Well, the mercury that is in coal-fired power plants flue gases, as well as in taconite industry flue gas, most of them, goes up in the air and it settles over the landscape. Where? In our lakes, in our rivers, and on our land, and accumulated in biomass that stays around the peat in the rivers and the sediment at the bottom. Keep that in mind when we talk about this and sulfate. What has this got to do with mercury? Whoops. So anyway, I'd like to first talk about where is the sulfate. This is an environmental issue, as well as a social impact and a health issue. For those of you that don't, whoops. I'll get to the right slide here and push the right button. There we go. So those that you don't know, this is the lightning bolt that's the Mesabi Iron Range, right? Okay, put your fingers on the right spot. That right in the middle there, the purple spots are mining features. Okay, the red spots are water discharges from mining features. That one in the middle I was showing you, that's the Mintac tailings basin. Way down here is the Canaseo pit. Right up here is the Dunka pit, North Shore Mining, right on the shores of Birch Lake, my lake. And then the yellow dots are the concentration of sulfate at certain discharge points. The bigger the dot, the higher the concentration. As you can see, down here at Fond du Lac tribal lands, the dots get smaller, diluted. But where does the concentrations come from? Partridge River by Aurora. This is Spring Mine Creek that probably none of you have heard about. It's on the Salo Road between Babbitt and Embarrass, and it's where we get our test water from. This is the Sand River, that the headwaters are the Mintac Tailings Basin. This is the Dark River. Pete's sakes. This flows up the Sand River into Lake Vermilion Pike Bay, which is classified as impacted impaired waters because of sulfate. Where does it come from? You can see that. Dark River goes up into Voyager. Spring Mine Creek goes down Embarrass River to the St. Louis River and on down to Lake Superior. As you can see, there are not many big yellow dots, but that is where the sulfate comes from. What happens when that sulfate flows downstream? It's a little bit of a science lesson for y'all. In their slow moving streams and rivers and swamps, you accumulate biomass at the bottom. Might call it mud. It's really a lot of biological matter there that does not decompose because it lacks oxygen. It's anaerobic, oxic, no oxygen, no decomposition. Until you have high sulfate in the surface water. Sulfate is SO4, 4 oxygens for 1 sulfur. And we got some really smart bacteria called sulfate reducing bacteria. They're down in the mud here, and they know really good when there's no other oxygen, they will steal the oxygen from the sulfate and eat the organic matter. That's how they survive. A couple things happen with that. Their byproduct is H2S, hydrogen sulfide. You would recognize it. It's that rotten egg smell. Nobody likes it. Smells pretty bad. It's the hydrogen sulfide that damages the wild rice, not the sulfate. But that organic, those sulfate reducing bacteria, when they're eating up that organic matter and breathing in the oxygen from the sulfate, are decomposing the biomass. When you decompose the biomass, what happens? You have a little bit of carbon dioxide. You release nitrogen, you release phosphorus. And remember that mercury that went up in the flue gases and settled down and everything that got sequestered in that biomass? You release the mercury. Now that's elemental mercury. It's not too bad. It's stuff, little balls you play around in your hands. Not when some of you were little, but when I was little. But those sulfate reducing bacteria do something else. They take that mercury and they don't want it. So they methylate it. They turn it into methyl mercury. Because that's soluble in water, not elemental mercury, but methyl mercury is. So it gets in the water, gets in the food chain, it's accumulated in the fat of fish. And we eat the fish, and accumulates in us. And that's why the St. Louis River and many other rivers and lakes have a limit on the recommendation of eating fish. And that mercury gets in the water, probably not totally, but to a big degree because of the sulfate. Now, if there is iron available, the right kind of iron, then we'll bond with the hydrogen sulfide and make iron sulfide. Pyrite, fool's gold, that type of stuff, pretty inert, okay, staying there so long as it doesn't get in contact with oxygen. Okay, enough of a science lesson on that. So that's why, that's what happens to sulfate in nature, okay? But what can we do about it after that? And that's where we come in with a system that mimics what nature does. We build. These bioreactors, here you see them, the real life one that's up at area 5 of the old Erie mine, the headwaters at Spring Mine Creek. These are individual modules, 7 foot by 7 foot on the surface, 12 feet deep, that sit in an old taconite mine pit lake. That's the mine pit lake, that's the headwaters of Spring Mine Creek, one of those major contributors. That one, 1,200 milligrams per liter against a sulfate standard of 10. Okay. We build those bioreactors, they have lots of surface area in them. There's very low oxygen in there, there's no mercury there. And why do we suspend them in the water? So they stay below the ice. They don't freeze in the wintertime, they can operate as well in winter as in summer. And our process then is modular with bioreactors, large surface area where the sulfate reducing bacteria attach to the surface area. They convert sulfate to hydrogen sulfide. It flows to another unit where we add iron. I call it reactive iron. Well, you want to touch and feel it. This is reactive iron, 97% pure iron. As Mike said, that's DRI, direct reduced iron, that we should be making here on the Iron Range. That actually came from Brazil via Jamaica, via South Carolina to Minnesota. But we need to make that here. It's the exact same stuff that Form Energy needs for their batteries. We use it because it's reactive, it's pure iron. And we release that iron and mobilize it with electrodes to bond with the hydrogen sulfide to make iron sulfide, which is what we then collect, the black stuff in that jar. That's what we make. We can pump that off, get it out of the system, it'll never go back to sulfate, and it has value. That material can be used for remediation of groundwater where you have chlorinated solvents, nitrated explosives, some stuff like that. My business partner sells stuff like that for groundwater remediation. The other place it can be used is to strip mercury out of the flue gas for coal-fired power plants and taconite processing plants. And it can also be used as a soil amendment for corn growing, because all it is iron and sulfur, which they need. So with that, it is possible to remove the sulfate if you want to dewater a mine pit lake to recover more of the mineral. Or for existing mine pit lakes that are seeping out and running downstream, causing those big contaminations we saw, such as the Mintac tailings basin, such as the 15 mine pit lakes on the old Erie mine site and other ones, and tailings basins. And yes, you can meet the sulfate standard if you do that. And I just like as the final thing to read from the Tribal Wild Rice Task Force. Okay? Because this is significant for social justice related to the Native American tribes. It is related to us being environmentally conscientious and health aware. If this can cut down on the mercury in our water, I think it's good. And so they say in that, excuse me for reading it, but I think it's important. These are their words, not mine. Virtually all of Minnesota waters that are not impacted by industrial discharge have sulfate concentrations below 10 milligrams per liter wild rice sulfate standard. Therefore, if industrial discharges were controlled in accordance with the law to meet Minnesota water quality standards, most domestic wastewater discharge for sewer systems and all that, would not require additional treatment to comply with the wild rice sulfate standard. Domestic dischargers that draw drinking water from source water where sulfate concentrates are elevated from industrial activities, mine pit lakes, only about 80% of range cities get their water from mine pit lakes. It's quite a bit. Could reduce the cost by treating potable water to reduce sulfate instead of adding treatment for wastewater. In addition to reducing costs, treating potable water would have community health benefits. That's why we think, along with all this greening of iron and steel, we're going to be doing more related iron on the Iron Range. We believe we should address this issue as well. That's all.
I think we're done at one.
Yeah, but I think we can
Right.
handle a couple of
So
questions.
before we leave, we understand, but we'll be here for questions as long as people have questions. There is my timer, right? Keeping the country. Here we go.
I will ask if you have a question that you say it into the mic.
Yes, go ahead.
Yeah, you're welcome.
Yeah, I just have a question on a sulfate. I know you mentioned that sulfate standard will be 10 milligrams per liter. Is it on a wild rice bed? Is that where that standard comes from?
The standard of 10 milligrams per liter been debated tremendously, but it is the standard, and it is the standard for any water discharges going into waters that produce wild rice or have produced wild rice in the past.
Wonderful. Any other questions? Oh, they'll talk that.
I have a question. I don't know if it applies, but you mentioned making steel at the mouth of the mine earlier on. And I'm wondering, is steel in that discussion a kind of a generic? I mean, it seems like steel is made into a lot of different forms. And so can you make an initial steel that's then convertible into other steel forms depending on the use?
But Eric, are you still online?
I am. Yeah, what the molten oxide electrolysis process does is it just makes raw steel. And then the question would be, well, what alloys and that sort of thing do you want to make with it? And that would be, yeah, I would want to refer to a metallurgist about those kinds of things. But the heavy lift, energy wise, is getting the iron and the oxygen separated. And that once you've got that, you've got green steel. Then whatever you want to do with it, it's up to you.
Can I ask you a question? I'd just like to add to that, for most of these processes, we wouldn't really call it steel we're making it, you're really making pig iron. That is the first step in that, then yes, you can do other sorts of different grades of that. And of interest, there's about 8 million metric tons of pig iron still imported into our country. So any additional pig iron that we could make would actually reduce dramatically our imports. And just of interest in that, I learned a week ago that in 2021, the biggest source of pig iron for the United States, number 1, Russia, number 2, Ukraine, number 3, Brazil. Needless to say, in 2022, Russia and Ukraine are not the top sources any longer. Now it's Brazil, just of interest.
Could I add to that? If I could add to that really briefly, anybody here know where the term pig iron came from? I didn't. I'm a vet, for God's sake. So when they pour molten iron out of the bottom of a blast furnace, it trickles down into little teeny ingots that look just like piglets that are sucking on mom. And that's where you get pig iron.
We are learning so much here today.
So let's assume that all of these different cutting edge technologies are doable and work. It seemed on one hand, it would be a no-brainer to bring all this here. On the other hand, it's going to take a crap load of money to build this infrastructure for all of these different processes. And this year, Minnesota had a lot of extra money. Was some of this ever brought to the legislature? Or is it just is this just too much dreaming we got going on here? How real is this?
Sorry, I'm monopolizing on this here a little bit, but one of the important things to understand on that is that on the positive side, the greening of iron and steel is happening. Go to the SME conference in Virginia back in April. And there, the whole industry is talking about it, and it is happening. Because it is more economic, not more expensive. And they need to be retiring these old blast furnaces because they're old. And they need to be doing it. So that investment is going to happen. It is happening now. The question we're addressing here is, where is that going to happen? I'm from Babbitt. Is it going to happen in Babbitt? No, we don't process iron in Babbitt. We just mine it and ship it to Silver Bay. Is it going to happen in Ealing? No, it's not. It's going to happen downrange if it happens here. And there, the big hurdle we have to get over is the traditional steel industry is not here. It's in Pittsburgh, Toledo, Cleveland. It's in Toledo or Cleveland Cliffs makes DRI right now. So the big question is, where is it going to be? The investment is being made. So it's not a new, absolutely new cost.
Thank you. And I'm just going to add that you're right. It is a crap load of investment that was made by the state of Minnesota. And the investments that they made were not directed at these things. I think it was about $2.1 billion that was spent in investing in climate and environment in our state legislature. The federal government in August of last year passed the Inflation Reduction Act. How many people are aware of what that does? Please raise your hands. Okay, Most people are not aware of what the Inflation Reduction Act was. It was a misnomer. It really should have been called the once in your lifetime major investment in climate that Congress decided to do. And they dedicated $369 billion as the bottom end of that investment. It probably is going to be closer to $1 trillion, if not more. That's the investment that's happening since they passed that law last August, the 16th of August. There has been approximately 150 billion with a B invested by companies in America to build new clean energy industry and economy. That's just the beginning, and it's happened in less than a year. That's going to push what's going on here. And it's markets that push this. But the federal government is saying, we want to partner with you. We want to help with you. Please make it happen in America. And the process of making iron ore and taking it to places, digging it out of the ground, processing it, creating it into pellets, moving it again to the lakes, moving it again down the lakes to another facility, reheating it, putting it through the chemical process, and then producing the steel. How many times do you have to handle it? Who here still heats with wood? Okay, you understand the process? Okay, how many times do you like to move the wood pile? Yeah, okay. Well, I did it for 2 years and then I said, I'm done. I went electric. So that's my point. The less times you have to move it, the cheaper it is. The less times you have to heat it up, the cheaper it is. And that's what's going to drive this. That's what's going to drive this, is when Cliffs and US Steel say there's a better way.
One very fast addition. The other policy that will support these market forces is putting the price on carbon.
Yes.
And that's CPL's major goal in life, is to promote that. But those are the policies. Promoting 100% clean energy, price on carbon, and market forces. That's what's going to move this. Any other questions?
Thank you so much.